Hi everyone. Today I am going to discuss a little bit about the result we have obtained so far in our research. But first, I would like to start with the background. Do you know there are more than 200 million different chemicals all around us, and the European Chemical Database alone contains data on more than about 150,000 different unique chemicals. Some are harmless, but some are very harmful to us and to our environment. In this study, we explore a group of chemicals known as persistent and mobile chemical, or in short, you are free to call them PM chemical. These chemicals have a unique characteristics. They can stay in the environment for extended periods and have the ability to move around, eventually accumulating in our water system, the water we drink. Imagine releasing these chemicals into the environment. They could persist for centuries, potentially affecting us and other living organisms. One famous category within PM chemical is PFAS, a group that has gained significant attention due to its widespread use within the human society. You can see the PFAS in your food containing material, in your vehicle, in your textile, everywhere. You can find PFAS examples. In our study, we have identified 64 PM chemicals, all considered potential threat to European drinking water sources. Among them, there are 24 PFAS, 17 triazines, and 23 triazoles. Now, let us consider this scenario. You are about to purchase a non-stick frying pan. We all love it, and you are concerned about its environmental impact. Wrong side of it. Someone might ask you, if you want to know more about, just go and perform an life cycle assessment, perform an LCA so you can know what are the impact there. But here is the catch. To include the toxicity impact of a chemical in your LCA, you need something called characterization factor. Think of characterization factor like conversion rates. Imagine you are dealing with climate change impact, which we often represent as carbon footprint in common knowledge. Now, climate change is not only caused by carbon dioxide, it involves other gases like methane, nitrous oxide, each with its own contribution. Here is where the magic happens. We used to a conversion factor to convert one gas to another. For example, we use a factor of value 29 to translate methane emission into equivalent amount of carbon dioxide emission and so on to calculate total carbon footprint. Now let us apply this idea to characterization factor. Think of characterization factors as those essential conversion rates that allow us to standardize different chemical impact onto a common scale. This common scale is what helps us to calculate the total chemical impact, creating what we can call a chemical footprint, similar to what we call carbon footprint. Now, there is a consensus within the scientific community, the big people, to use a tool called USTOX to find these characterization factors. But, and it is big, but this tool needs data, a lot of data. In its database, they have characterization factor for around 2,500 chemicals for environmental toxicity. But guess what? Out of over 64 small number of chemicals, they only have 18 characterization factor in their database, and none of them were PFAS. To calculate characterization factor, we need data on fate, exposure, and effect. These data can be challenging to obtain, especially when it comes to toxicity data. So we consider varied database for physical and chemical property and also collected toxicity data from sources like Comtox, EcoSAR, and more. But that is not all. We realize that these PM chemicals might have transformation products, which could also be relevant. In our screening exercise, we identified 322 transformation products using various tools. Then we filter out these products, narrowing down to 79 based on their persistence, which are more persistent than their parent compound. And at last, we found three transformation products that are both persistent and more toxic than their parent compound. This promoted us to include them in our characterization factor calculation. So now in total, we have 65 chemical in our study to calculate characterization factor. Now here is a thing about ecotoxicity data. It is complex, like it has, you have to think about different species, endpoint, study duration, and then you have to harmonize. We harmonize this data, making it consistent and ready for analysis. Now let's go to the finding of our study. First, we can discover that out of a total 64 chemical, we Consider in our study, experimental data is only available for 47. This led us to rely on in silico tool to fill data gap for 17 chemicals. This indicates a significant challenge, a lack of data for calculating characterization factor, and so we move forward how we can fill the data gaps. Next, when we compare our calculated effect factor to those in the UStock database, we observe something different. The correlation was not high. This suggests that as we incorporate new data sources within the characterization factor calculation, characterization factor became dynamic rather than static. In other words, you can say the characterization factor are influenced by the ever-evolving landscape of data, highlighting the importance of regular updates. Moving on to the third set of results, which revolve around data harmonization. These stocks typically require chronic EC50 data, which is not always readily available. In our study, we took a detailed approach to harmonization, considering different species and various effects. Interestingly, despite our detailed efforts, we found that simplified harmonization can still capture the main picture regarding characterization factor. This does not mean that detailed harmonization is not valuable, but it does show that when resources are limited, a simplified approach can be sufficient to capture the big picture. Now let's talk about the fourth and the final set of results. We compare experimental data with estimated data, and the correlation was surprisingly low. This suggests a need for caution when using estimated data, especially as available QSAR model may not be entirely accurate for characterization factor calculation. Our recommendation, whenever possible, opt for the experimental data if available and accessible. If you are not able to get the experimental data, then to fill the data gap, we can go to find estimated data. In conclusion, our study provides characterization factor that can be invaluable for including these chemical in LCA studies. By doing so, we enhance the accuracy of ecotoxicity assessment and these critical data gaps. So these chemicals can be included in LCA. And as we continue to advance in science and technology, our understanding of these chemicals and their impact will keep evolving. In the end, it is all about making informed choices for a cleaner, safer, and more sustainable world. Thank you for joining us on this journey of scientific exploration and knowledge. And in next video, we will come with a new findings in our research project. Till then, please follow our channel ZeroPM and hope to see you again. Thank you very much.
0PM, Zero Pollution of Persistent and Mobile Substances. This project has received funding from the European Union's Horizon 2020 Research and Innovation Programme under Grant Agreement number 101036756.